In the previous 3 lectures, we've discussed various techniques of integration. So we've considered logs and exponentials, hyperbolic functions, sines, cosines, etc. These were all smooth, differentiable, continuous functions. In this lecture, we're going to consider the situation where the integrand contains a discontinuous function or perhaps a singularity. A singularity is where a function blows up, becomes infinite. In that situation, an integral may exist or it may not exist. Finding out whether it does or does not is going to be very important. And so let's begin with discontinuous functions. Let's begin with this example of the discontinuous function that you have before you. It is clearly discontinuous because it is jumping from 0 to 1, then from 1 to 2, and then from 2 to 3, and so forth. Actually, we can write down a formula for it. F of x is n, provided that x lies in the interval between n and n minus 1. So, for example, if n is 1, then if x is between 0 and 1, then its value is 1. And then it becomes 2 and 3 and so forth. Now, to complete the definition of the function, we have to say what it is elsewhere. So I'm just going to say that f of x is 0 elsewhere. And elsewhere here on the real line means that x equal to 0, x equal to 1, 2, and so forth. Now, clearly, this is a function that cannot be differentiated except when it is clearly flat over here. So, where it is flat, the derivative is 0. Here, here, here. But if I'm at x equal to 1 or x equal to 2 or x equal to 3, then clearly it cannot be differentiated. That limit of f of x plus epsilon minus f of x divided by epsilon does not exist. On the other hand, the integral does exist. So let's look at this area between 0 and 1. That's 1 unit. That's 2 units. That's 3 units. Now let me define the area A as a function of x as being the integral of f of s from 0 up till x. You can see that if x is 1, then over here the area is 1. When x becomes 2, the area becomes 3, and so forth. In between the integers, you can see that it rises linearly, and it's all connected. So f is clearly discontinuous, but you can see from the graph that A is continuous. And as you remember, continuous means that the limit from the left and the limit from the right are equal. And that's true for every point on this curve over here. So A is a continuous function, although f was discontinuous. Now let's take another discontinuous function. In this case, I'm simply going to define f of x to be n if x is equal to n, and n here is 0, 1, 2, 3, 4, etc. It's 0 elsewhere. And so here, what would you expect the derivative to be? It is 0 between 0 and 1 in the open interval between 0 and 1, but at x equal to 1 it doesn't exist, at x equal to 2 it doesn't exist, and so forth. What about the area as a function of x? Well, you could have anticipated the answer. A of x is 0 everywhere. It is a completely flat line lying along the x-axis. Why is that? Well, basically because there is no area under this point over here. You could think of a little maybe rectangle whose width has shrunk to 0. Of course, all of this we've done much more rigorously when we talked about the Riemann integral. But the point here is that for this function, which is horribly discontinuous, the integral is nevertheless continuous. It's 0. Now, more generally, integration smooths a function. So, if f of x is put into an integrating machine or an integrator, and f of x looks like this, it goes up, comes down, it's clearly broken. Nevertheless, what comes out of the integrator, in other words, the integral from some fixed value up till x over here, this is why you have a function of x here. That function of x is connected, it's smooth, it's continuous. And so it could be very well possible that the integral of a discontinuous function is a continuous function. On the other hand, you see that differentiation gives edges. It roughens up a function. So if you were to take this function and put it back as input into a differentiator, then the differentiator will take the derivative of the function. So if you take the derivative at this point, it's 0. If you take the derivative at this point over here, that's a constant value. So while the line is sloping upwards, it will have a constant value. That's over here. Then the derivative here is again 0, which is why you go back to 0. And then it goes up to 1 or some constant value. Hence, you get a non-zero value here and so forth. So the point is that the differentiation then gives edges to a function that's relatively smooth. Let me now prove a theorem that's going to be important for the rest of this lecture. Suppose f of x can be integrated on the interval from a to b and is therefore integrable, and that its maximum value is capital M, its minimum value is small m. In that case, the value of the integral from a to b of f has to be less than m times the length of the interval, which is b minus a, and it has to be greater than or equal to small m times b minus a. Now, you remember that when we discussed the Riemann integral some lectures ago, what we discussed was that the integral from a to b of f has to be less than or equal to the upper sum, and it has to be greater than or equal to the lower sum. As we make a partition finer and finer, the lower and the upper sums become closer and closer, and their common value will be the integral. Now, just to remind you, here is the picture that I had used earlier. You can see that the maximum value of the function is this, f of x3, and the minimum value of the function is f of x0. So in other words, m is f of x3 and small m is f of x0. And the function integrated between a to b has to be less than m times b minus a and greater than m times b minus a. Now, this is clearly true in the present case because if one looks at m times b minus a, that is this area which I'm drawing over here. And this is the area under the curve, under this black curve over here, all the way up till the point B. And clearly that area is bigger than m times b minus a, and it's less than m times b minus a, which is, of course, just this area. So all the area that is over here, that's m times b minus a. So this theorem is actually very obvious, but it's helpful for us to prove the next theorem. The next theorem states that if f of x is integrable on a, b, and we define capital F as a function of x, and this x occurs over here, then capital F is a continuous function on AB. We're not saying that this is continuous, by no means, but we are saying that capital F is continuous. What does continuity mean? As we've discussed many times before, continuity means that capital F plus epsilon becomes f of x in the limit that epsilon becomes very, very small. In this particular function, f of x plus epsilon is the integral from a to x plus epsilon, f of s ds. And now I'm going to break this up into two parts, a to x, and then the second part is x to x plus epsilon. That's actually very easy to see. So, for example, if you have a function like this, then this is a, and this is x, and this is x plus epsilon, then the total area of the curve between a and x plus epsilon is the sum of this area and the sum of this area. Now, this part over here is obviously just f of x, and so we have f of x plus epsilon is f of x plus this other integral, x to x plus epsilon. And now the point is that we can use our theorem, which says that this here has to be less than or equal to the maximum value of the function f, let's call that m, times the size of the interval, which is epsilon. Now, as epsilon goes to 0, no matter what the value of m is, as long as it is finite, in that case, f of x plus epsilon gets closer and closer to f of x, and hence we have shown that capital F is a continuous function. The important thing was that f of s has to be bounded, and if it is bounded, then certainly you can integrate the function small f in the interval a to b. Let me now come to the second part of the lecture, in which we shall deal with integrals having singular integrands. What that means is that if we're considering an integral like this, integral a to b of the integral of f of x, somewhere in the interval between a and b, and possibly at the endpoints, the function f becomes infinite. So let me take the first example. Here is a function that becomes infinite at x equal to 0. You can see that there is a square root of 0 at the bottom, which is a 0. And this integral, we want to know if it exists or not. What about this one? And here the problem is not at x equal to 0, the problem is at x equal to 1. Here is another integral with a problem with a singularity, in other words, at x equal to 1. And although there is no x minus 1 factor over here, you know that when x becomes close to 0, the logarithm of x goes to infinity. So, do these integrals exist? How will we know? What should we do in order to decide on this question? The question of the existence of an integral takes us to the topic of convergent and divergent integrals. Now, suppose f of x is a function that's singular at the point x equals capital F. So let me, for the sake of being definite, take the closed interval a to b, and let's say that x is some point which is between a and b. It could even be at small a, or it could be at small b. And at this point, the integrand small f blows up, is infinite. Now, we want to know if the integral exists. And so we shall define f of epsilon to be the integral of f from a up to some point which is close to x. Now remember that epsilon can be positive or negative. The integral is said to exist or converge if f of epsilon approaches f of 0 as epsilon goes to 0. Otherwise, it is said not to exist or to diverge. Now, for understanding this well enough, we shall need to take a number of examples. As our first example, let's take the integral of 1 over square root of x. Now clearly there is a problem over here because the integrand is blowing up at x equal to 0. In other words, as we come in from x equals 1 towards x equals 0, the integrand is going to infinity. So instead of doing the integral up above, we should look at epsilon to 1 dx x to the power minus half. And now that's very easy to do because the answer is just 2x to the power half, and we need to evaluate this between epsilon and 1, and that's just 2 minus 2 square root of epsilon. So epsilon to the power half. As epsilon goes to 0, we can see that this integral goes to 2. And so the integral exists, certainly, and the limit is also something that we found. It's 2. As our second example, let me take the integral of 1 over 1 minus x from 0 to 1. Here the problem is not at x equal to 0, but rather at x equal to 1. So, instead of studying the integral up above, let me look at the integral of 1 over 1 minus x, but stop just a little bit short of x equals 1. This integral is very easy to do. It is just minus log of 1 minus x. And that's because if you differentiate log of 1 minus x, you get minus 1 over 1 minus x, and this minus sign here takes that into account. We must evaluate this between x equals 0 and x equals 1 minus epsilon. And so this becomes minus log of epsilon plus log of 1. The log of 1 is no problem, it's just 0. But there is a problem over here because you see that when epsilon goes to 0, log of epsilon goes to minus infinity, and so this goes to infinity. In other words, this integral does not converge. Or you could say it does not exist. Let's now look at this integral, The problem here is obviously close to x equal to 2. So let us stop the integration by going close to x equal to 2, but stopping just short of it. Now this integral can be done. The answer is obviously minus 1 over x minus 2. And now this has to be evaluated between 0 and 2 minus epsilon. The result of which, when we put x equal to 2 minus epsilon at the top, is 1 over epsilon. And when you put x equal to 0 at the bottom, that's minus 1 over 2. Now, clearly this goes to infinity as epsilon goes to 0. And so this integral does not exist. The integral of log x has no problem at the upper limit, but when x is close to 0, then log of 0 is minus infinity. So therefore, let us consider epsilon to 1 of the integral of log of x. But the integral of log of x is something we've done many times. It's just x log x minus x. And if you differentiate what's inside, you'll just get log of x. The limits are between epsilon and 1. Log of 1 is 0, and so this is just minus 1 minus epsilon log of epsilon plus epsilon. Of course, we're only interested in small epsilon, and therefore this will be neglected. All we need to know is what is the limit as epsilon goes to 0 of minus epsilon log epsilon. There are many ways of doing this, but there's one that I find very easy, and if I put epsilon equal to e to the power minus y, then as y goes to infinity, epsilon goes to 0. So this is the limit as y goes to infinity of y into e to the power minus y, or y over e to the y. But this is 0, because you remember when we discussed the exponential function, we discovered that the exponential e to the power y becomes much, much bigger than any power of y as y becomes large. And so this integral is fine. It exists. In this third part of the lecture, I'm going to deal with integrals that have infinite limits. What that means is, I want to know what is the meaning of the integral of f where the upper limit is infinity, or what is the meaning of this integral where the lower limit is minus infinity. To this end, let us define capital F of x as being the integral of f from some fixed value a all the way up till capital X, where this capital X is bigger than the lower value. Now, if we make x, capital X, larger and larger, and if that limit exists, then we say the integral converges, and that the value of the integral a to infinity is the limit as x tends to infinity of this integral from here to x. Let's now look at possibilities. So you could have, for example, the integral of 1 over square root of x from 1 to infinity, or you could have the integral of 1 over x, or you could have 1 over x minus 1 squared, or you could have the integral of 1 over log x. Let's see whether, in fact, these integrals with infinite limits actually exist, or whether they don't exist, or in other words, diverge. As our first example, I want to ask whether this integral exists. I'm not asking for its exact value, merely whether this converges. And so we can save ourselves a lot of trouble and a lot of work by recognizing that as x becomes larger and larger, this becomes closer and closer to square root of x. In other words, log of x can be neglected. Therefore, what we need to do is integrate up till capital X dx over square root of x. And that, as we recognized earlier, is 2x to the power half, and we're only concerned with the upper limit, that is 2 square root of x. And now as x goes to infinity, this goes to infinity. So this integral does not exist. What about this integral? Does it exist? It has a huge number, 10 to the power 9 in the denominator, but that will not save this integral because x can become much, much bigger than 10 to the power 9. Of course, 1 over x is very, very small, and so we can neglect this in the limit where x becomes large. In other words, as we approach the upper limit of integration. And so what we really need to do is just consider this integral. Well, this integral is log of x. And log of x goes to infinity as x goes to infinity. So again, this integral does not exist. What about this integral? Does it exist? Now, for large values of x, that is at the upper range of integration, the 2 does not matter. And so really we need worry only about x to the power 1 plus epsilon. And this is just x to the power minus epsilon over 1 plus epsilon. As x goes to infinity, this goes to 0, provided that this epsilon is positive. So, even if epsilon is 0.01 or it is 0.00001, this integral will converge. The integral before you has an integrand that is singular both at x equal to 0 and at x equal to 1. At x equal to 0, we have log of 0 over here. And at x equals 1, the log over here has argument 0. So there's a problem at both ends. Well, let's make a change of variables. X is e to the minus y, in which case when x is 0, y clearly has to be infinity. That's because e to the minus infinity is 0. And when x is 1, y is 0. E to the 0 is 1. The change of variables brings to us dx is minus e to the minus y dy. And so let's put that into the integral. So the integral becomes now infinity. So we're integrating on y. Y goes from infinity to 0. And there's a minus dy e to the minus y. That's because I've substituted dx equals minus e to the minus y dy. And then there's the log of minus log of x, which is log of y. Let me just change the limits of integration so that it looks a little nicer. This becomes 0 to infinity dy e to the minus y log of y. You remember that integral a to b is minus integral from b to a. Okay, we still now have a problem at both ends. At the top end, log of y goes to infinity. And at the lower end, when y is 0, log of y becomes infinity again. Let's treat the two separately. So at the upper limit, so let's look at the infinity limit, the upper limit. In that case, I'm just going to look at the limit as x becomes infinite, and I have e to the minus y log of y. But log of y is a number that's always going to be less than y. We've talked about this earlier. So this, for large values of y, and notice that I'm not talking about the lower limit because we're just interested in the upper limit over here. So we have dy and e to the minus y, y. And we can integrate this very easily. This is just minus y e to the minus y plus e to the minus y. You can see that if I differentiate this, then I get y e to the minus y. And this has to be evaluated at y equal to x. So this is minus x plus 1 into e to the minus x. And as x becomes larger and larger, that goes to 0. So as x goes to infinity, e to the minus infinity will make this go to 0. This x plus 1 doesn't matter because the exponential grows faster than any power of x, and we can make this e to the minus x, just put it in the denominator if you're not happy with this. So at the upper limit, the integral converges. What about the lower limit? At the lower limit, we need to deal with this integral, epsilon e to the minus y log y. We don't need to worry about the upper limit over here because that is certainly finite. And now e to the minus y we can replace with 1 because when y gets very, very small, remember that epsilon is going to 0 now, this is going to be like dy log of y. But that's the integral that we've just looked at. And as epsilon goes to 0, this will go to 0 in the limit epsilon tends to 0. And so this integral exists. We have not found its value, but it is certainly a convergent integral, and that's all that we wanted to know. Finally, we want to consider integrals which have infinite limits at both ends. So the integral of f from minus infinity to plus infinity can be broken up into an integral from minus infinity to 0, that's over here, and from 0 to infinity. If these separately converge, according to the procedure that we just discussed, then the integral we want is just the sum of these two integrals. Let's take some examples. Look at this one. The denominator is going to be a problem at large values of x, and you see that if x becomes very large, then we can just forget about this 1 and this square root of magnitude of x. And so basically we just concerned here about dx over x up till capital X, and now capital X is going to become very, very large, and so this becomes log of x that goes to infinity as x goes to infinity. And so this integral does not exist. Let's now look at this one. Here, the integral that we want is dx over x squared. The 1 doesn't matter at large values of x, up till x. And now this is minus 1 over capital X, and this then will go to 0 as x goes to infinity. And yes, this integral does exist. Of course, you have to look at the other end too, but this is a symmetric integrand, so you know what that answer will be as well. Now look at this one. Here we have e to the minus magnitude of x. So let's consider the positive values of x first. That's e to the minus x, and going all the way up till capital X. Now this is just minus e to the minus x, and when we put capital X equal to x, this becomes e to the minus x. That goes to 0 as x goes to infinity. So yes, this integral does exist. Now again, this is a symmetric function. If you change x to minus x because of the magnitude sign over here, you would find that you have exactly the same thing as over here. Of course, if this magnitude sign was not there, then the integral would blow up at minus infinity. And finally, let's look at this one, e to the minus x squared. Unfortunately, I do not know what is e to the minus x squared dx. That is, as an indefinite integral. This means that I cannot use the method that I had used up above by doing an integration. Instead, what I must do is consider the fact that e to the minus x squared has to be less than e to the minus x, and hence this integral must be less than e to the minus x dx, and the same limit over here. Now, when capital X goes to infinity, this goes to 0, just like above over here, and so this integral also converges. It does exist. Note that here we are saying that the integrand over here is less than the integrand over here, and hence the integral to the left and the integral to the right are therefore connected together, in the sense that if this one over here exists, then certainly this has to exist. In a future lecture, we're going to talk about how an integral can be evaluated numerically using a computer. But before one comes to that, it's so important to know whether that integral which one is trying to calculate on the computer actually exists or not. And this is why in this lecture we did so many examples of different functions and found that some could exist and some cannot. That was really the purpose of this lecture.